Hey students, guess what time it is? It's science time. Get out your notes and let's start learning. All right, hopefully the last one wasn't too bad. So this next question is a continuation from the previous one. So we'll need the same data that we had with the last question. So a continuation from it. So number 3, from the previous problem, after 1.2 seconds and 3.5 seconds, find the following information. How high is the ball? What is the current range of the ball? Is the ball rising or falling? How fast is the ball traveling vertically and horizontally? What is the vector of the ball? In other words, what is the velocity and direction? So we're looking for the resulting velocity and the direction at those points in time. So what you're going to be doing is you're going to find all the information for 1.2 seconds and 3.5 seconds. So what I'm going to do is I'm first going to solve for the 1.2 seconds. I'll explain what's going on along the way, and then I'm going to have you solve for the 3.5 seconds. So let's go ahead and get started. All right, for the next part of the problem. From the previous problem, after 1.2 seconds and 3.5 seconds, find the following information. How high is the ball? What is the current range of the ball? Is the ball rising or falling? How fast is the ball traveling vertically and horizontally? What is the vector of the ball? So in other words, we're trying to solve for what is the resulting velocity and direction of the ball at that point in time. Now, this is a continuation from the last problem. We had a ball that was being shot off at 50 meters per second at a 30-degree angle. We took that, we broke it down into its x and y components. So we found out it was going 43.3 meters per second horizontally and 25 meters per second vertically. At halfway through its flight, when it reaches the highest point, it would have traveled vertically at 31.89 meters, and it would have reached that highest elevation at 2.55 seconds. Now it's taken another 2.55 seconds for it to fall back down, which means it would have landed at 5.1 seconds, and the total distance it would have traveled was 220.83 meters. Now, in this problem, what we're looking for is at 1.2 seconds, basically what's happening to the ball. We want to find out everything as to what's going on with the ball. How high is it? How far has it traveled? What is the velocity? What is the resulting velocity of it? Is it going up or down? What direction and what angle is it going? So if you look at this, we can actually kind of use the previous information as a means of somewhat checking your work, just to see whether or not it's within the ballpark. So at 1.2 seconds, so at time 0, it's starting here, and at 2.55 seconds, it's going to be over here. So at time 1.2 seconds, it's going to be somewhere on this side of this half of its part of its travel here. So I'm just going to put a circle here. Let me make this a little bit darker. Okay, so this is a time of 1.2 seconds. So just from looking at this, we do know the ball should be going up. But let's pretend we didn't know that. Okay, and we only have this information here. We know we have a ball going at 50 meters per second at a 30-degree angle at 1.2 seconds. How high is the ball? How far? What's the current range of the ball? Is the ball going up or down? Now, if I'm looking at this, we know it should be going up. But how would you know that if you didn't know this information? So I'm going to show you how to go about figuring that part out. And also, what angle is the ball going at that point in time? And what is the resulting velocity of that ball? And then ultimately, what you're going to be doing is you're going to be figuring out at 3.5 seconds. Now, if I'm looking at this, this is 2.55, this is 5.1. So at 3.5 seconds, we do know it's going to be somewhere over here. So when I'm done with this, you're going to be figuring out this part over here. Okay, so watch how I go about solving for this, and listen to the explanations, and that will help you answer this part over here. So let's go ahead and get started. So what we always start with first is your givens. So givens, and we want to break this down into its x and its y components. Alright, now for the x components, what do we know? We do know it's 43.3. So the velocity in the x direction is 43.3 meters per second. Do we know anything else in the x direction? Now keep in mind, we're not using this, okay? We're pretending as though we don't know this. But there is one other bit of information we do know, is time. Previously, we didn't know what time would it land. You had to solve for this. This time, I want to know at 1.2 seconds, where is it at? So we do know time. The time is 1.2 seconds. Now, because we have velocity and we also have time, and we're dealing with the x direction, we can go ahead and solve for the distance in the x direction. And there's only one formula that we have to be concerned about in the x direction, is velocity is equal to distance over time. And again, we're dealing with velocity in the x direction and solving for the distance in the x direction. So to rearrange this, all we're doing is distance is equal to the velocity times time. And again, we're looking at the velocity in the x direction. So distance in the x direction is equal to the velocity, which is 43.3 meters per second. Make sure you put your units in here. And a time of 1.2 seconds. Maybe knows seconds will cancel out, leaves you with the unit of meters. So the distance in the x direction will come out to be 51.96 meters. So if you multiply those, so we would have gotten this distance right here, 51.96 meters. That means at this point in time, let me change colors here. At this point in time, this projectile would have traveled horizontally at 51.96 meters across at 1.2 seconds. So we still need to figure out how high is it, and also how fast and what direction is it going. So let's go ahead and do that next. So let's solve for our givens in the y direction. In the y direction, the Vy, the initial velocity, is 25 meters per second. The time is still 1.2 seconds. Alright, the acceleration, because it's going up, it's going to be decelerating at negative 9.8 meters per second squared. Now, let me also point something out to you here too. Because it's first going up at 25 meters per second, going upward, we do know the direction of this. And because it's going against gravity, it's always going to be negative 9.8. And even though it's coming back down, it's going to be accelerating positive 9.8 on the way back down. You'll still keep this as negative 9.8. Because if you play around with this number right here, one thing you'll see here is as this number gets larger, as time goes on, the velocity is also going to be getting larger as well. It actually, if you plot it out, or if you put in a whole series of numbers, you'll see the numbers, the velocity will start getting smaller, and then also the velocity will start getting larger. So you leave this, because it's first initially going up at negative 9.8, you leave this as a negative value. Doesn't matter what the time is here. Okay? So when you're doing your part of this, keep it the same thing here. The only thing you'll be changing is this value right here, is the 1.2 seconds. Okay? So, and basically we just need to solve for everything here. I want to know what is the final velocity of it, because it's not going up to the very top. It's not going to be 0. It's still going to have an upward velocity taking place with this. So we don't know what is the velocity of this. We also don't know what's the distance in the y direction. Okay, and I think that's about it for this part of it here. And so what you're going to do is you're going to go ahead and use your basic acceleration formulas here that you've already been using many times before. So let's see, let's go ahead and solve for the distance. How high would this go up? And the one equation that we can possibly use to solve for the distance in the y direction is d is equal to, let me bring this up a little bit, VIT plus 1/2 AT squared. Okay, so if you plug in the numbers, the initial velocity is 25 meters per second. The time is 1.2 seconds. Plus 1/2. The acceleration is negative 9.8 meters per second squared. And the time is 1.2 seconds squared. Okay. Now make sure you leave this again as a negative value. So when you multiply these two values together, you multiply all these, because this is a negative value, these two values are going to be subtracting here. You'll end up getting a value of about 22.944 meters. So that's the distance in the y direction. So that's this value right here. The d sub y is 22.944 meters. So that'll tell you how high is it. Okay, so we know how far out has it traveled and how far up has it traveled, or what's this vertical point over here. So the next thing, let me go and put these values in here. So we have 22.944 meters. We have this distance is 51.96 meters. So let's go ahead and solve for the velocity. Okay. So for the velocity, again, there's more than one way. You could now use like possibly two different formulas here, but using the information that we already have with our givens, I'm going to use EF is equal to EI plus AT. Okay, and we're just solving for the final velocity. So the final velocity is equal to the initial velocity, which is 25 meters per second, plus the acceleration is negative 9.8 meters per second squared, and the time is 1.2 seconds. So we end up getting a final velocity of, what was it, 13.24 meters per second. And if you look at the units, one of the seconds will cancel out, and meters per second, so the unit is still going to be meters per second. So the velocity is 13.24 meters per second. Now, one thing I want to point out to you about here is this also gives you not only how fast is it going, but also what direction is it going. Because this is came out to be a positive value. This is a positive value. Let me put it underneath here. Positive would equal up. If you get a negative velocity, because velocity is a vector, and it has a direction and a magnitude to it, but the direction also has can be a positive or negative value, just depending upon what direction. So in this type of setup, if you end up with a negative value, that would mean it's going down. Now, because this is going 13.24 and it's a positive value, I also know what direction is it going. So this is going 13.24 meters per second up. okay, or in the X direction here. So from this, I do know that this velocity, I'm going to change colors here. So at this point in time, this vector is going 13.24 meters per second up vertically. But how fast is it going horizontally? Now, if you remember, all projectiles, the horizontal component always remains the same. So it's still going 43.3. So it's going up at 13.24. It's going across horizontally at 43.3. All right. So now we are almost there. So let me just kind of quickly recap. We're able to use the velocity and the time to solve for what is the horizontal range. So we got 51.96. And then using the fact that it's going up at 25 meters per second, it's a projectile going up and eventually it's going to start coming back down. But at 1.2 seconds into its flight, and because it's acting against gravity, so the value is negative, we can find out at this point in time it's going 13.24 meters per second, but because this is a positive value, that means it's going upward. And we can also solve for vertically, it's going to be 22.944 meters upward. So the only thing that's left is what is the vector of this ball at this point in time. So let's go ahead and work this part out. So to do this, I'm just going to switch over to a new sheet of paper here and just concentrate on this aspect of it. So we have a vector that is going across at 43.3. It's going up at 13.24. Okay, and so from those two things, we can then figure out the resultant of this, because the actual path of this ball is going to be the resultant of these two vectors. And because they're right angles, it makes things a bit easier. So at that point in time, this ball is going to be traveling something like this. Pretend that's a straight line. So this is going to be, we're going to find out what is the resulting velocity and also what is its angle. So I'll put this away for a moment. So let's go ahead and work this one out. So if you notice here, we have a right angle triangle, and this is 13.24, which means that this side is also 13.24 meters per second. This is also up here at the top is 43.3 because it's a parallelogram, and the resulting velocity is the hypotenuse. And if you remember, an easy way of doing this is probably using just Pythagorean theorem. So this, since the resulting velocity is the hypotenuse of the triangle, so VR is equal to the square root of, basically what we're doing here is we're taking the Vx squared plus Vy squared. So we're taking the Vy and this being the Vx, and we're going to use that to solve for the resulting velocity. So this is your c squared, or c is equal to square root of a squared plus b squared, basically. So to solve for this, we're just going to plug in the values. So Vx is 43.3. I'm going to square that. And my Vy is 13.24 meters per second. And I also want to square that. And once I get the sum of those two squares, I want to take the square root of that value. And just by looking at this, you should be able to kind of get a rough idea and end up getting a value of 45.28 meters per second. So at that point in time, this projectile is going 45.28 meters per second. And if you look at the diagram, that should seem somewhat reasonable. Remember, the resultant should be greater than this value here, but no greater than the sum of those two values. Remember back when we were going over kind of the early days of vectors. So that's how fast it's going to be going. So the next thing is, what is the angle of it? So try not to use this information here, but we do have 13.24 and we have 43.3. So if we're trying to solve for this, this is your opposite, this is your adjacent, so we're going to be using tangent. So the next part is tangent theta is equal to opposite over adjacent. And so I'm just going to plug in the values here. Tangent theta, my opposite is 13.24 meters per second. And then the adjacent is 43.3 meters per second. And I'm trying to solve for theta. So I need to get rid of tangent. So I need to take the inverse tangent on both sides. Make sure your calculator is in degree mode when you're doing this. So you're going to take the inverse tangent at 13.24 all over 43.3 meters per second. And when I do that, I end up getting a value basically about 17 degrees. So that means this angle here is a 17-degree angle. So that's my angle. So the resultant of this vector, my resulting velocity, is 45.28 meters per second at 17 degrees above horizontal. Okay. So what does that mean? Let me bring it back to this here. So that means at that point in time, when this thing is, I pretend that's a nice triangle here, at this point in time, this projectile is going at a 17-degree angle, and it is going at 45.28 meters per second. Okay, and this is kind of helpful, especially if you're trying to aim for a certain type of target. And let me go switch back to the other one here. Actually, let me go down here. So what that means, in fact, it's going at a 17-degree angle at that point in time. And break this down into the X and Y components here. At that point in time, when it's flying through the air, this resultant is going to be tangent to that arc. Okay, so always remember this resulting velocity is going to be tangent to this path here. And I can't draw that exactly here, but pretend that's a tangent line. So as though if you were to extend that the line straight down, it would only touch that arc at only one point, and then it will come back off on this side, still remain on this side without crossing over to the other side. And if you're trying to shoot at a target, or if you're trying to get this thing to go into a hole or something like that, the most ideal direction to have a ring, for example, like a loop for the pass through here, is to have a loop that's going to be perpendicular to that. So in other words, if I had a loop for this thing to pass through here, I would want that loop to be perpendicular to that point here. So in other words, if I looked at it from a side view, I want this loop to be perpendicular to that circle. And it's kind of think like in basketball. If you have a loop like this, now if you try to throw a ball, so here's your backboard. If you try to throw a ball like this, chances are it's not going to do so good. And if you've ever played basketball, you might be familiar with this. The better way of doing this is to kind of lob it up a little bit, to have it go on something like this. And this way, it's going to be a little bit more perpendicular to that. By making the path of this more perpendicular to the ring itself here, it's more likely to be able to go through. It actually has a bigger area for it to be able to pass through. The most ideal will be dropping it straight down, which would be nearly impossible to do here. But the more vertical it is at that point in time, the better chance it has of passing through that hoop. So your next task is to do this. Is I like for you figure out at 3.5 seconds. That's over here. The same information. I want to know what is the horizontal component, what is the vertical component. Be able to tell me if it's going up or down. So if up or down. And then what is the resulting vector of this? In other words, how fast is it going? Basically kind of like what I did here. And also what angle is it going at that point in time? So it's going to be exactly the same thing that we just did here. The only difference you're really making here, instead of using 1.2, is you're going to be using 3.5 seconds instead. So give that a go, and hopefully you'll do well on that. If you have any questions, be sure to email me, and I will talk to you later. Make sure you like, subscribe, and share this with all your friends. I plan on going viral someday. Well, hopefully not anymore. I think we're done with viruses here, but you get the idea. All right, you guys take care. Bye-bye. So hopefully you did well on the problem that you had to work out. So we're going to go ahead and solve for the problem for 3.5 seconds and see how well did you do with that information. So we have, come on now, we have a projectile. We know it's going at 43.3 meters per second horizontally. It's being thrown upward at 25 meters per second. We want to know at 3.5 seconds, where is it at? Now, I'm going to approach this a little bit differently, where I'm not drawing out the whole thing, and I'm just going to put it over here. So time is 3.5 seconds. Okay, so we don't know if it's still going up or if it's coming back down, but technically we do know, but let's pretend as though in this situation we don't. So let's start with the givens. So the givens, and let's look first at the x direction. So the only thing we know in the x direction is the velocity in the x direction is 43.3. That's your velocity in the x direction. And this is your velocity in the y direction. And the time is 3.5 seconds. So let's solve for the distance in the x direction. So this way we can find out at this point in time, what is its range. So using the basic velocity formula, velocity is equal to distance over time. And this is velocity in the x direction, distance in the x direction. So the distance, or the range, is equal to the velocity times time. Again, this is velocity in the x direction. So the distance is equal to the velocity is 43.3 meters per second, and the time is 3.5 seconds. Seconds cancel out, leaves you with the unit of meters. So the distance is 151.55 meters. I hope I did that correctly. So we have this value here. So that tells us the range, the distance in the x direction at this point in time is 151.55 meters away from where it was first thrown. Alright, so this is the information in the x direction. For the givens in the y direction, the initial velocity in the y direction is 25 meters per second. The acceleration, because it's being thrown upward, is going to be negative 9.8 meters per second squared. And we have a time of 3.5 seconds. So basically, we want to know what is its final velocity in the y direction, and what is the distance in the y direction. What's this vertical component of it? And then ultimately, we'll find out also what direction is it going at that point in time. So let's first solve for the distance in the y direction. You may solve for the velocity, that's fine. So the distance in the y direction, so just d sub y, I'm going to be using bit plus 1/2 at squared. So plugging in the formula here, the initial velocity is 25 meters per second. The time is 3.5 seconds plus 1/2. The acceleration is negative 9.8 meters per second squared. And I'm going to run out of room here. And the time is, I'll put it down here, 3.5 seconds mean squared. Now again, remember, you want to keep this acceleration still negative. It'll still work out fine. And when you solve for the distance in the y direction, you get a value of 27.475 meters. That means at this point in time, this projectile is 27.475 meters in the y direction. Now, pretending like we don't know, we still don't know if this is still going up or if it's coming back down. So it could be, if this is all the information you had, this thing could still be still rising up. Or this could have already reached its peak and it was coming back down. Now technically we already know that, but pretending as though we don't. So that's the way we find out, is with looking at the velocity. Now, let me also point out too, if you ever end up with a negative distance, that means the projectile has now gone below ground. So the fact that it's positive value simply means it's still above ground. If this is still above ground. If you ever end up with a negative displacement, that means it went underground, or in the very least, it's below the area where it was thrown. So, solve for the velocity. Vf is equal to vi plus at. And the final velocity is equal to the initial velocity, which was 25 meters per second, plus the acceleration, which is negative 9.8 meters per second squared, and a time of 3.5 seconds. So the final velocity comes out to be a negative 9.3 meters per second. Now, this negative value here means that it is going down. Positive means it's going up. So that not only does it tell us how fast we're going, but also what direction do we have to draw that vector. So that is the other bit of information that we have here. So at this point in time, it's going downward at 9.3 meters per second. The negative just simply indicates what direction is it going. So now, using those 2 points of information, let me redraw this. So we have a downward velocity of 9.3. Now if you left this as negative, that's okay. It really doesn't matter here. It's just being used as a means of indicating direction. And horizontally, if you remember, horizontally, the velocity does not change. So it remains at 43.3 meters per second. So we're going to break this down into its x and y components. Pretend that's a straight line. Actually, I didn't do so bad on that one. We're going to solve for what is the resulting velocity and what is the angle below the horizontal, from the horizontal. So we're going to be using Pythagorean theorem. So VR is equal to the square root of 43.3 meters per second squared plus 9.3 meters per second. And again, if you use negative here because you have to square it, it's not going to matter. And the resulting velocity is 44.29 meters per second. So that gives us the velocity that's going at that point in time. So at this point in time, it is going at 44.29 meters per second. And if you look at it, this seems kind of reasonable. Again, this is not drawn to scale. This should be larger than 43.3, but it cannot be larger than the sum of these two values. And then in order to solve for the angle, we have to use tangent. So tangent theta is equal to opposite over adjacent. So tangent theta, the opposite is 9.3. And the adjacent is 43.3 meters per second. So we're solving for theta. So theta is equal to the inverse tangent of 9.3 meters per second over 43.3 meters per second. And end up getting a value of about 12.12 degrees. And this will be below horizontal. So this angle is about a 12.12 degree angle below the horizontal. So at that point in time, during this projectile's path, we now know it's going to be going downward, and this path is going to be, this line right here is going to be tangent to that arc. So at that point in time, it's going 44.29 meters per second, and it's going to be traveling at a 12.12 degree angle below the horizontal. So if I were to set up a ring, say a hoop for it to pass through, the most ideal position would be where it's going to be perpendicular to that direction. In other words, I want to have a loop that's going to be perpendicular. It's perpendicular to that direction here. Actually, that should be going from the resulting vector. Okay, so hopefully you did well, and we will be continuing on. If you have any questions, feel free to contact me. Either email me. I can also set up a Zoom if some people would like to get some extra assistance here too. So hopefully all of you are doing well, and you guys have a great day. We'll talk to you later. Bye-bye.